Hello everyone. Electric charges and fields part 5 problems. In this video, I'll be discussing some of the problems which are given in the exercise section of the NCERT text. So, this is the first problem. What is the force between two small charged spheres having charges of 2 into 10 raised to minus 7 coulomb and 3 into 10 raised to minus 7 coulomb? Placed 30 centimeter in the air. In this, we can use the Coulomb's law to find the force between these two small charged spheres, and it will be equal to 6 into 10 raised to minus 3 Newton, and it is a repulsive force. These are the steps for doing this problem. First, we can write the charge on the first sphere Q1 is equal to 2 into 10 raised to minus 7 coulomb. Charge on the second coulomb Q2 is equal to 3 into 10 raised to minus 7 coulomb. Now distance between the spheres R is equal to 30 centimeter, which is 0.3 meter, since we have to convert it into the SI system. Now electrostatic force between the spheres is given by the relation F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square, which is the Coulomb's force law. And here epsilon 0 is known as the permittivity of free space, and the value of 1 by 4 pi epsilon 0 is equal to 9 into 10 raised to 9 Newton meter square Coulomb raised to minus 2. Therefore, force F is equal to, we get the answer as 6 into 10 raised to minus 3 Newton. Hence, force between two small charge spheres is 6 into 10 raised to minus 3 Newton. The charges are of same nature. Hence, force between them will be repulsive. Now, the second problem. The electrostatic force on a small sphere of charge 0.4 mu coulomb due to another small sphere of charge negative 0.8 mu coulomb in air is 0.2 Newton. What is the distance between the two spheres? And B, what is the force on the second sphere due to the first? In this problem also, we can make use of the Coulomb's force law. Now, electrostatic force on the first sphere F is given as 0.2 Newton. Now, charge on the sphere Q1 is equal to 0.4 microcoulomb, that is 0.4 into 10 raised to minus 6 coulomb. Now, charge on the second sphere Q2 is equal to minus 8 into 10 raised to minus 6 coulomb. Now, electrostatic force between the spheres is given by the relation 1 by 4 pi epsilon 0 into Q1 Q2 by R square. By using this equation, we can find the value of R square. That is, R square is equal to 1 by 4 pi epsilon 0 into Q1 Q2 by F. Now, substituting the values, we get the value as 0.12 meter. Now, for the second part of this problem, both the spheres attract each other with the same force. Therefore, the force on the second sphere due to the first is 0.2 Newton. Now we can see the third problem. Check that the ratio K E square by capital G into ME into MP is dimensionless. Look up a table of physical constants and determine the value of this ratio. What does the ratio signify? The given ratio is K E square by GME MP, where G is the gravitational constant. Its unit is Newton meter square, kilogram raised to minus 2. Me and MP are the masses of electron and proton. In their unit is kilogram. E is the electric charge and its unit is coulomb. And K is equal to 1 by 4 pi epsilon 0. And its unit is Newton meter square, coulomb raised to minus 2. Therefore, unit of the given ratio is equal to m raised to 0, L raised to 0, T raised to 0. Hence, the given ratio is dimensionless. Now, substituting the values of all these constants, we get the value as 2.3 into 10 raised to 39. This is the ratio of electric force to the gravitational force between a proton and an electron, keeping distance between them constant. Fourth question. For point charges, QA is equal to 2 microcoulomb, QB is equal to minus 5 microcoulomb, P is equal to 2 microcoulomb, and QD is equal to minus 5 microcoulomb are located at the corners of a square ABCD of side 10 cm. What is the force on charge of 1 microcoulomb placed at the center of the square? This is the square. Now, the given figure shows a square of side 10 cm, that is equal to 0.1 meter. Now, the sides AB is equal to BC is equal to CD is equal to AD is equal to 10 centimeter, while the diagonals AC is equal to BD is equal to 10 root 2 centimeter by using Pythagoras theorem. A charge of amount 1 microcoulomb is now placed at point O. Force of repulsion between charges placed at corner A and center O is equal in magnitude but opposite in direction relative to the force of repulsion between the charges placed at corner C and center O. Hence, they will cancel each other. Similarly, force of attraction between charges placed at corner B and center O is equal in magnitude but opposite in direction relative to the force of attraction between the charges placed at corner D and center O. Hence, they will also cancel each other. Therefore, the net force caused by the four charges placed at the corner of the square or 1 microcoulomb charge at center O is 0. Now, the fifth problem. In this case, there are 2 point charges QA and QB, which are 3 microcoulomb and negative 3 microcoulomb, which are placed 20 centimeter apart. Now, it is required to find the electric field at the midpoint O. If a negative test charge of magnitude 1.5 into 10 raised to negative 9 coulomb is placed at this point, what is the force experienced by the test charge? Now, the situation is represented in the figure. O is the midpoint of line AB, and distance between the two charges is already given as 20 cm. Therefore, AO is equal to OB is equal to 10 cm. Now, the net electric field E is equal to the electric field at O caused by plus 3 microcoulomb charge E1, which is equal to 1 by 4 pi epsilon 0 into 3 into 10 raised to minus 6 by R square, which is 10 into 10 raised to minus 2 the whole square along OB. Similarly, field due to the charge negative 3 microcoulomb charge is also given by 1 by 4 pi epsilon 0 minus 3 into 10 raised to minus 6 by OB square. And this is also along OB. Hence, the net electric field at O is given by E1 plus E2. Since the magnitudes of E1 and E2 are equal and in the same direction, E is equal to 2 into 9 into 10 raised to 9 into 3 into 10 raised to minus 6 by 10 into 10 raised to minus 2 the whole square Newton by Coulomb, which is equal to 5.4 into 10 raised to 6 Newton per Coulomb along OB. Therefore, the electric field at midpoint O is 5.4 into 10 raised to 6 Newton per Coulomb along OB. Now for the second part, which is the B part. When a test charge of 1.5 into 10 raised to minus 9 Coulomb is placed at O. In this case, The force experienced by the test charge F is equal to Q into E. That's equal to 1.5 into 10 raised to minus 9 into 5.4 into 10 raised to 6. That's equal to 8.1 into 10 raised to minus 3 Newton. The force is directed along line OA. This is because the negative test charge is repelled by the charge placed at point B but attracted toward point A. Therefore, the force experienced by the test charge is 8.1 into 10 raised to minus 3 Newton along OA. Now, the sixth problem. A system has two charges. QA is equal to 2.5 into 10 raised to minus 7 coulomb and QB is equal to minus 2.5 into 10 raised to minus 7 coulomb. Located at points A 0, 0, minus 15 centimeter and B 0, 0, 15 centimeter respectively. What are the total charge and electric dipole moment of the system? This is an electric dipole. As we can see, it consists of two charges having opposite polarities and they are kept as shown in this figure. There is at positions negative 15 centimeter along the z axis and positive 15 centimeter also along the z axis. So at A, the amount of charge QA is equal to 2.5 into 10 raised to minus 7 coulomb and at B, QB is equal to negative 2.5 into 10 raised to minus 7 coulomb. Now the total charge of the system is 0. Distance between these two charges is given by 15 plus 15 is equal to 30 or 0.3 meter. Therefore, the electric dipole moment of the system is given by dipole moment P is equal to QA into D, which is equal to QB into D, which is equal to 7.5 into 10 raised to minus 8 coulomb meter along the positive z axis. Therefore, the electric dipole moment of the system is 7.5 into 10 raised to negative 8 coulomb meter along positive z axis. Now the seventh problem. For that, consider a uniform electric field E is equal to 3 into 10 raised to 3 I cap Newton per coulomb. What is the flux of this field through a square 10 centimeter on a side whose plane is parallel to the YZ plane? What is the flux through the same square if the normal to its plane makes a 60-degree angle with the x-axis? In this case, the electric field intensity is given as 3 into 10 raised to 3 I cap. Therefore, magnitude of the electric field intensity is equal to 3 into 10 raised to 3 Newton per coulomb. Now, side of this square is equal to S is equal to 10 centimeter, which is equal to 0.1 meter. The area of this square is given by A is equal to S square. That's equal to 0.01 meter square. The plane of the square is parallel to the YZ plane. Hence, the angle between the unit vector normal to the plane and electric field theta is equal to 0 degree. Therefore, flux through the plane is given by the relation phi is equal to EA cos theta. That's equal to 3 into 10 raised to 3 into 0.01 into cos 0 degree. That's equal to 30 Newton meter square per coulomb. Now, when it makes an angle 60 degree with the plane, then we substitute cos theta is equal to cos 60 degree and we get the answer 15 Newton meter square per coulomb. Now, eighth question. Careful measurement of the electric field at the surface of a black box indicates that the net outward flux through the surface of box is 8 into 10 raised to 3 Newton meter square per coulomb. what is the net charge inside the box. If the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or why not? In this, we can use the Gauss's law. The net outward flux through the surface of the box phi is equal to 8 into 10 raised to 3 Newton meter square per coulomb. For a body containing a net charge q, flux is given by the relation phi is equal to q by epsilon 0, where epsilon 0 is the permittivity of free space. Hence q, which is the charge enclosed, is equal to epsilon 0 phi, which is equal to substituting the value of permittivity of free space, which is 8.854 into 10 raised to minus 12 Newton raised to minus 1 coulomb square meter raised to minus 2, we get 7.08 into 10 raised to minus 8 coulomb, or 0.07 microcoulomb. Now the answer to the second part is no. Net flux piercing out through a body depends on the net charge contained in the body. If net flux is 0, then it can be inferred that net charge inside the body is 0. The body may have equal amount of positive and negative charges. Now the ninth problem. A point charge plus 10 microcoulomb is at a distance 5 cm directly above the center of a square of side 10 cm as shown. What is the magnitude of the electric flux through the square? For that, we can think of the square as one face of a cube with edge 10 cm. So according to Gauss's theorem for a cube, the total electric flux is through all its 6 phases. That is 5 total is equal to q by epsilon 0. Hence the electric flux through one phase of the cube, that is through the square, is phi is equal to 5 total by 6, or 1 by 6 q by epsilon 0. Now substituting the values, we get the answer as 1.88 into 10 raised to 5 Newton meter square per coulomb. Now the 10th problem. In this case, a point charge causes an electric flux of negative 1 into 10 raised to 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 cm radius centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? What is the value of the point charge? Now electric flux phi is equal to is given that it is negative 1 into 10 raised to 3 Newton meter square per coulomb, and radius of the Gaussian surface r is equal to 10 cm. Now electric flux piercing out through a surface depends on the net charge enclosed inside a body. It does not depend on the size of the body. If the radius of the Gaussian surface is doubled, then the flux passing through the surface remains the same. That is negative 10 raised to 3 Newton meter square per coulomb. Now for this second part, electric flux is given by the relation phi is equal to q by epsilon 0 by Gauss's law. Now substituting the values, we get the answer as negative 8.854 nanocoulomb. Now the 11th problem. A conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is 1.5 into 10 raised to 3 Newton per coulomb and points radially inward, what is the net charge on the sphere? Now electric field intensity at a distance for a sphere is given by E is equal to 1 by 4 pi epsilon 0 into q by d square, where d is the distance from the center, which is 0.2 meter, and 1 by 4 pi epsilon 0 is equal to 9 into 10 raised to 9. Substituting the values, we get the value for Q. Q is equal to E into 4 pi epsilon 0 into D squared, which is equal to 6.67 nanocoulomb. Now 12th problem. A uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter square. Find the charge on the sphere. What is the total electric flux leaving the surface of the sphere? Now the diameter of the sphere is given, radius of the sphere is given. Now surface charge density sigma is equal to 80 into 10 raised to minus 6 coulomb per meter square. Therefore, the total charge on the surface of the sphere Q is equal to charge density into surface area, that's equal to sigma into 4 pi r square. Therefore, the charge on the sphere is 1.447 into 10 raised to minus 3 coulomb. For the second part, what is the total electric flux leaving the surface of the sphere? We can use the Gauss's law. That is phi total is equal to Q by epsilon 0. Now substituting the values for Q and epsilon 0, we get the value as phi total is equal to 1.63 into 10 raised to 8 Newton Coulomb raised to minus 1 meter square. Therefore, the total electric flux leaving the surface of the sphere is 1.63 into 10 raised to 8 Newton Coulomb raised to minus 1 meter square. Now for the 13th problem. An infinite line charge produces a field density of 9 into 10 raised to 4 Newton per Coulomb at a distance of 2 cm. Calculate the linear charge density. Linear charge density is given by lambda. Now the electric field produced by a infinite line charge at a distance d having linear charge density lambda is given by the relation E is equal to lambda by 2 pi epsilon 0 d, which implies lambda is equal to 2 pi epsilon 0 d E, where d is equal to 2 centimeter, which is equal to 0.02 meter, and the value of electric intensity is already given as 9 into 10 raised to 4 Newton per Coulomb. And the value of 1 by 4 pi epsilon 0 is equal to 9 into 10 raised to 9. Now substituting the values, we get the value of lambda as 10 microcoulomb per meter. Therefore, the linear charge density is 10 microcoulomb per meter. Now the 14th problem. Two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite signs and of magnitudes 17 into 10 raised to minus 22 coulomb per meter square. What is electric field intensity? A. In the outer region of the first plate. B. In the outer region of the second plate. C. Between the plates. So this figure shows two plates which are kept parallel to each other, and there are three sections, namely section 1, section 2 and section 3. A and B are two parallel plates close to each other. Outer region of plate A is labeled 1, outer region of plate B is labeled as 3. The region between the plates are labeled as 2. Now the charge density of plate A is 17 into 10 raised to minus 22 coulomb per meter square, and that of B is negative 17 into 10 raised to minus 22 coulomb per meter square. In regions 1 and 3, the electric field is 0. This is because charge is not enclosed by the respective plates. Therefore, electric field in region 2 is given by the relation E is equal to sigma by epsilon 0, where epsilon 0 is the permittivity of free space. Substituting the values, we get the electric field intensity between the plates is equal to 1.92 into 10 raised to minus 10 Newton per Coulomb. Therefore, electric field between the plates is 1.92 into 10 raised to minus 10 Newton per Coulomb. So this is the end of this video. In this video, I have discussed some problems which were related to electric fields and charges. If you have got any doubt, please comment in the section below. Thank you.